Optimal allocation and size selection of dispersed generation in radial distribution system. Abstract. This paper contributes an analytical technique for the allocation and size selection of dispersed generations, DGS, in radial distributed system, DS. The proposed technique is computationally expeditious as compared to other existing techniques. The prime objective of this method is to improve voltage profile at each node and reduce total active power loss in 33-bus radial distribution system, RDS. Voltage stability indicator, VSI, is used to find heavily loaded bus in the system. After finding the heavily loaded bus, it is set as optimal location for placement of DG. At this optimal location, the size of DG is determined by using continuous increment of step size, CISS, technique. The effectiveness of the proposed technique is validated from simulated results, by comparing voltage profile, branch current, and power losses with the presence and absence of DG. Keywords: radial distribution system, dispersed generation, optimal allocation, voltage stability indicator, continuous increment of step size. Introduction. In recent era, distribution system, DS, is added as an integral part of power distribution system 1. The indispensable growth of power demand has increased the role and importance of DS. To encounter the load demand effectively, several changes occur in DS resulting in establishment of complex distribution structure. One of the most important changes in DS structure is invasion of renewable energy in the system. These invasions are known as dispersed generations, DGS. The involvement of DGS in the system affect DS such as minimization of power loss, improvement of node voltage, and reliability too. Thus, DS in accordance with DG is the most prominent part of research domain. Most of the DS structures are radial in nature in which power flows in a single way from the distribution substation to the consumer. 3. Radial distribution system, RDS, has high ratio, radial structure, and unbalanced conditions of load wherein are the resistance and reactance of line respectively. High ratio leads to high power loss and more voltage drops. In RDS nodes, sudden voltage drops occurs under critical loading conditions. In transmission system, load flow by traditional methodologies has serious convergence problems due to the high ratio of the RDS. For proper RDS planning, an efficient load flow technique is required. Hence, these methodologies are substituted by the available methods for load flow of distribution system as backward-forward 4 and direct approach methods 5. These methods have the advantages of quick convergence and less computation time. /Rx. In conventional system, renewable energy invasion has increased in earlier years due to environmental concerns. The conventional generation resources such as thermal, hydro, nuclear, etc. are being penetrated by small-scale generations like photovoltaic, PV, wind, and fuel cell. Although these DGS have very less capacity, range, 1 kW to 50 MW, compared to other conventional resources, availability of these resources minimize power loss, improves voltage profile 6. Therefore, DGS are required for optimal sizing and proper location. Many researchers have found proper solution of optimal sizing and location issues of DGS and DS. Genetic algorithm, GA, is implemented to solve the meta-heuristic optimization problem for location and size selection of DG7. The technique used in 8 minimizes the fitness function using GA for power loss minimization. In general, constant power models are considered in the DS. But in 9, different load models i.e. residential, commercial, and industrial are carried out in RDS while optimally allocating and sizing DGS using GA. A hybridized GA and simulated annealing, SA, algorithm is implemented to compute optimal location of DG in 10. A mixed GA particle swarm optimization, GAPSO, algorithm is mentioned in 11 to find out the optimal location and sizing of DG. In 12, 13, binary PSO and fuzzy embedded GA techniques are proposed for optimal DS planning in presence of DGS. The problem of optimal DS planning with DGS in 14 is treated by means of multi-objective PSO, MOPSO. A MOPSO approach is employed to deal with problem considering different load models in 15. Artificial bee colony, ABC, algorithm is employed to determine the optimal allocation, size, and power factor in order to minimize active power loss 16. Bacterial foraging algorithm, BFA, is implemented to find the optimal size of DG17. In 18, backtracking search algorithm, BSA, is used to assign DGS and DS. An immune algorithm, IA, is formulated to solve the optimal DG planning problem in Smart Grid 19. Modified teaching learning-based algorithm, MDLBA, is proposed in 20 to compute the optimal allocation and size of the DG units in RDS. Although numerous techniques are available for optimal location and sizing of DG, but traditional techniques are still a current interest. Thus, this article presented a voltage stability indicator, VSI, which indicates the heavily loaded bus. This bus signifies the optimal location of DG placement. After proper allocation of DG, the size of DG is found out by continuous increment of step size, CISS, technique. CISS technique is applied to monitor active and reactive power loss in the IEEE 33 bus system. The paper is organized as follows. In section 2, presents load flow equations and power loss computation for 33 bus roads. Proposed methodology for optimal allocation and size selection of DG are explained in section 3. Section 4 discusses the 33 bus test system and simulation results. Finally, conclusion is outlined in section 5. 2. Problem formulation. A radial distribution load flow. In 5, author proposed a simplified and efficient technique for radial distribution system, RDS. A simplified RDS shown in Fig 1. The equivalent load current injection, corresponding to power injection equations. 3. Proposed methodology. In distribution system, the node voltage plays an important role to maintain good voltage regulation. Ideally, voltage regulation should be nearly equal to 0, but due to line resistance and reactance there are slight drop in voltage in different nodes of the RDS. To improve voltage profile and reduce line losses, different DGS are used at different power factor 21 according to the requirement as shown in table. A voltage stability node indicator for DG placement. To identify the most sensitive or heavily loaded bus in the system, voltage stability node indicator, VSNI, is used. From figure 1 branch current is given by. From 11, it can be cleared that. Further, when the value of the VSNI approaches to 1.0, the system will become unstable. Similarly, the values away from 0 indicates improved stability of the system. 01 VSNI. B. Optimal size selection using continuous increment of step size, CISS. Once the optimal location of DG is fixed, then DG size change from 0 to 1 pu of the total load. As the DG size increases, total active power is injected to the system increases. This injected power minimizes the total active power loss. A parabolic curve is formed between DG size and total active power loss. This curve indicates, first the losses of the system decreases till it reaches the optimum point. Thereafter, system losses suddenly increases. Thus, step size plays factor while selecting DG size. In present scenario, the step size chosen is 0.1 MW. For exact DG size, step size must be as small as possible, but the simulation time increases. Start tread load and line data run load flow compute VSNI for each bus and choose maximum value. Fix the location of DG at maximum value of VSNI bus. Initially set the DG value PDG equals P load and rerun the load flow compute PTL save, K, TH iteration power loss is PTL, K, TH if PTL, K, TH PTL, K plus 1, TH save, K, TH iteration power loss is PTL, K, TH set PDG is optimal size stop noise. For result in discussions. The Fig 3 shows the single line diagram of 33 bus radial distribution system. The detailed methodology of the proposed method is described by flowchart as shown in Fig 2. The proposed flowchart described in 2 steps. At first, optimal location of DGS are calculated by using VSNI. The tabulated values of VSIN are shown in Table 1. The Table 1 indicates the active and reactive power consumed by different buses and their corresponding VSNI values. In next step, the optimal size of the DGS are determined by using continuous increment of step size, CISS, technique with a step size of 0.1 MW. A case A, DG placement at bus no. 25. In this case DGS are connected at bus number 25. From the Fig 4 it is noticed that, active power loss of the system increases, when the DG size increases beyond an optimum point. Optimal point is calculated based on values of voltage stability node indicator, which is shown in Table 2. 051015202530350102030405060 line no VS line loss no lean loss, KW, and DG. B case B, DG placement at bus number 24. From the VSNI table, it is clear that bus number 24 is the most critical or weakest bus of the system. This weakest bus identified as the optimal DG allocation point. Further, DG size is computed by using CISS technique. CKC, DG placement at bus no. 30. To examine the efficacy of the proposed technique, it is applied to 12.66 kV, 3.72 MW, and 2.3 bar RDS consisting of 33 buses. Further, after application of load flow the real power losses incurred by the system before placement of DGS is 210 kilowatts. To reduce the total power loss of the system DGS are placed at different locations as shown in Table 3. The optimal allocation point is computed by using 11. After computing VSIN at all buses, the 3 locations i.e. bus number 25, 24, and 30 identified as the most critical bus. To determine the optimum size, CISS technique is applied on all the critical buses. From Fig 4, 6, and 8, shows the curve between DG size and total power loss. It is basically follow a parabolic curve, first the total loss decreases and then increases. While selecting DG size, appropriate step size should be chosen carefully. DG size should not exceed the optimum value, above optimum value the total active power loss of the system increases. As a result, system operates in poor voltage regulation and efficiency. From Fig 5, 7, and 9 it clear that after placement of DG at optimal locations, the total active power loss reduced in 33 bus radial distribution system. Finally, Fig 10 shows the comparison of voltage profile at different optimal locations. The conclusion. In this paper, a mixed analytical method is presented on the impact of dispersed generation in RDS. In this method, VSNI and CISS were used to determine the exact location and compute the size of DGS respectively. Proposed method was tested for 33 bus RDS to reduce active power losses and improve voltage profile at each node. The results showed that clearly indicates that KC, allocation of DG at bus number 30, is found to be most appropriate location in minimizing the total active power loss and improving node voltage as compared to the other cases considered.